All right, so our first few questions, we're going to start off going pretty quickly because we did a lot of these in class. So if I can get this working right. There we are. So first one, as soon as we see sign of something with x and with y, we're immediately thinking implicit. So we do d dx of the first term, d dx of the second term. Again, we did this in class. The outside is sine, derivative of sine is cosine. We leave xy alone. And we multiply, this is the key, when we multiply by this box, it's product rule, but we need to have this in a big parentheses because it's going to distribute to both parts of the product. So the derivative of x is 1. We leave y alone. Then plus x we're going to leave alone. And then dy dx is the derivative of y. It's 1 dy dx, right? We only put the dy dx when we're actually doing the derivative of the y part, right? So when we have x times y, right? When we do the derivative of the x part, that's 1. We leave y alone. We don't put a dy dx there. Then plus we leave x alone. The derivative of y is 1 dy dx. It's because it's a y variable when we're taking the derivative with respect to x. So that's the one that gets it. Now all of this had to go into parentheses and multiply by cosine of xy. Then on the right side, the derivative of x is 1. From there, we just go ahead and distribute. You can kind of look at the steps. Y comes to the front, plus x cosine of xy times dy dx equals to 1. We're going to leave this on the right side, move this over to the left side. And we divide by x cosine of xy to both sides. And that gives us our answer. All right, next up we have another tangent line one. And what is the slope of the line tangent to the curve? So we're going to do the same thing. As soon as I see, slope, I'm thinking the word derivative. And then I have y squared and x squared, so I'm going to do d dx to both terms, or every single term. And the derivative of 3y squared is 6y dy dx minus the derivative of 2x squared 4x equals, I put a 0 here. And then the derivative of negative 2x is negative 2. And then y, we're going to leave alone. Plus then negative 2x, I'm going to leave alone. The derivative of y is dy dx. So this part was maybe the harder part for some people. And then I want to make sure that at this point I could, and a lot of people might do this, I could isolate for dy dx. Like I could isolate for dy dx and get dy dx equals something with x's and y's over something with x's and y's. But for me, whenever I have a point 3, 2, if I'm able to, I like to plug that in as soon as I can. I make less mistakes. And so anywhere I see a y, I'm going to plug in 2. And anywhere I see an x, I'm going to plug in 3. So I went ahead and just plugged in. 6 times 2 is 12. dy dx minus 4 times 3 is 12. Equals negative 4 minus 6 dy dx. Add the 6 dy dx over. Add the 12 over. 18 dy dx equals 8. dy dx is 8 over 18, simplifying to 4 over 9. Okay, this one we talked about in class, so I don't really feel like I need to go over it too much. I think we talked about this one pretty in-depth in class. Basically, D looks very close, but it was a possible inflection point. So to keep the video short, I'm going to move on. But if you have a question on 14, go ahead and put it in the chat, and we'll go through that. Next up, 43, an equation of the line tangent to y equals x cubed plus 3x squared at its point of inflection. So a lot of times they give you like at x equals 5 or at x equals 6 or at whatever. This time they didn't do that. They said at its point of inflection. So where do we get an inflection point? When y double prime equals 0. So I'm going to start off with kind of a blank x1, y1, and m. We don't know any of them. But I know that they want it at its point of inflection. So first I'm going to take the first derivative, 3x squared plus 6x. Then I'm going to take the second derivative, the derivative of that, 6x plus 6. And we're going to set this equal to 0. We subtract 6, divide by 6, we get x equals negative 1. So that's the first thing that I solve for. Then from there, now that I have this, now it's just like any normal tangent line. Right, so I'm going to just kind of ignore the fact that I've already taken the second derivative, just kind of go back up here. How would I do a tangent line? Well, to get y1, we just plug in negative 1 for x, right? Negative 1 cubed plus 3 times negative 1 squared plus 2. And I did that over here, and we got y1 was 4. And then to get m, just like any other time, we plug in negative 1 into the derivative. Well, 3 times negative 1 squared plus 6 times negative 1, I did that right here, gives negative 3. Now that I have all three of these, now I can do a y minus y1 equals m times x minus x1. I did that up here. And it is in mx plus b form. All the choices a, b, c, d are in mx plus b form. So I just distribute that. Y minus 4 is negative 3x minus 3. Add the 4 over, and it matches up with b. All right, 36. Consider all right circular cylinders for which the sum of the height and the circumference is 30 centimeters. What is the radius of the one with the maximum volume? So they want radius, and I see maximum volume. As soon as I see maximum volume, I know this is an optimization question. Right, I'm trying to maximize something. Optimization. So what do I want to maximize? I want to maximize the volume. So what that means is anytime I want a max or a minimum in Calc, we take the derivative, set it equal to 0. So the first thing they gave me was they told me that the sum, meaning I'm adding, the height and the circumference is 30 centimeters. That's h plus 2 pi r. I don't want to put h plus c. I need to know the formula. So h plus 2 pi r equals to 30. Now, this is my first equation. And then my second equation is my volume. Now, I want to take the derivative of this volume. Right? That one I need to take its derivative. But what I need is, I needed to have only one variable on the right side. And so this is like my main equation, my optimizing equation. But I'm going to use this guy over here as my supporting equation to replace one of the variables. So it looks way easier for me to solve for h than it does to solve for r. So I'm going to solve by h by just subtracting 2 pi r to both sides. And we take this and we plug it in for h into our main equation. So that's volume equals pi r squared times 30 minus 2 pi r. We'll go ahead and distribute. That gives us 30 pi r squared minus 2 pi squared r cubed. And then now, this is my equation in one variable. Now I can take the derivative. I like to put a line underneath it just to help myself realize I'm doing something different. So I take the derivative. 30 pi stays. Bring the 2 down. 2 times 30 is 60 pi r. Minus. Bring the 3 down. 3 times 2 is 6. Pi squared stays. It's just a constant. R squared. We're going to set that equal to 0. These have a 6 pi r in common. So I'm going to factor out a 6 pi r. And then I'm left with 10 minus pi r. When I set this part to 0, I get 6 pi r equal to 0, which is r is 0. When I set this part to 0, I get 10 minus pi r equals 0, which gives me r equals 10 over pi. Both of these are answers, but r equals 0 would kind of be an extraneous solution. It's a solution that I get extraneous, but it doesn't make any sense in the context of a problem. I can't have a cylinder with a radius of 0. It wouldn't be a cylinder. So this is the one that makes sense, and that's choice E. All right, next up, the derivative of a function is given by f prime of x equals x squared cosine of x squared. How many points of inflection do we have? So I'm going to go ahead and pop open our graph. And so we have the graph of x squared times trig cosine of x squared. And we're going to go ahead and graph that. And they gave us, this looks really crazy, but they gave us an interval. So I'm going to go to my window zoom and change my zoom. They said to go from -2 to +2. And now I can just kind of count. And, oh, you know what? I totally messed this up. So if you did this, you would get it wrong. I would have gotten 1, 2 times it changes. But I need to go back and take a look at this. It says the derivative is given by f prime. So I like to graph the derivative of that, right? I like to graph f double prime. The reason I like to graph f double prime is they're saying how many points of inflection, and that's where I can see the f double prime, I can see that the most clearly. Now, if I did graph this one, I could count for f prime, I could count minimums and maximums or inflection points. So it'd be one minimum, second one for the maximum, third one for the minimum, fourth one for the maximum, and fifth one for that minimum. So it is 5. But I'm going to go ahead and actually change this. So what I can do is, if I hold down Shift, the Shift key, and go right there with the left arrow, I can go Control X, will be a cut. It copies it, but it erases it at the same time. And I want the derivative of, then I'm going to go Control V to paste that back in. That way, this is the graph of f double prime. And then I can count the zeros where it changes. It's nice and easy. 1, 2, 3, 4, 5 are inflection points. Remember that for inflection points, it does need a pass through. So if any of these were those ones where it bounced back, it wouldn't work. So our answer is 5, choice E. All right, this one we talked about in class. I went over this. Directly proportional is y equals kx, and inversely proportional is y equals k over x. So we just kind of need to break it down. It says the rate of change of the volume with respect to time. That's dv dt. So dv dt needs to equal something. When you get rid of a, get rid of b. Is directly proportional to, so I can likely get rid of d because d looks like an inversely proportional, to the square root of the volume. So is directly proportional is going to be k times, they said the square root of the volume, not the square root of the time, so choice E. All right, next up we have a second derivative equation. And our second derivative equation is given by this, the second derivative is given by this equation f double prime of x equals x times x minus a times x minus b squared. And then the graph of f double prime is shown above. And for what values of x do we have a point of inflection? So again, point of inflection on a second derivative graph is where f double prime changes signs, right? It needs to pass through. And so A does pass through, 0 does pass through, B does not pass through, it bounces back there. So it's choice A, just 0 and A. All right, next up is our beloved related rate. I know that's always our favorite. And this one is probably the hardest related rate one, is the sine, cosine, tangent question. I think this is probably one of the hardest related rate questions for us, and just in general. So, as we read this, it says, if theta increases at a constant rate of 3 radians per minute, so that's d theta dt. I wrote that as one of my givens. At what rate is x increasing? So they want dx dt. That's what we want to find. When x equals 3. So I'm going to throw x equals 3 here. So then we have sine theta equals x over 5. That's what I started with. And the reason I chose sine theta is theta is here. Okay, x is my opposite, 5 is my hypotenuse. Those are the two I know about. So I chose sine theta equals x over 5. In this case, because they wrote 5 in, it's a constant, which is nice. So we can just write 5. We don't have to write over opposite, or opposite over hypotenuse, over c. We can just write over 5. So the first step is going to be to take the derivative with respect to t of both sides. The derivative of sine theta will be cosine theta times d theta dt. Don't forget about that, right? The reason it's times d theta dt is it's implicit. Theta is not the same variable as t. They're different variables, so we need to do that implicit part. Then the derivative of x over 5. Okay, x over 5 is kind of like the same thing as 1/5 x, 1/5 x. So the derivative with respect to t of 1/5 x is just 1/5, but then times, these variables don't match, so we need to do implicit dx dt. So that's how I got this right side. Now, for dx dt, that's what I want to solve for. D theta dt we know is 3, but we don't know cosine theta. So in order to get cosine theta, well, what is cosine theta? Is cosine theta is the adjacent over the hypotenuse. Well, I know the hypotenuse, that's 5, but I don't know this adjacent side. So I went ahead and called it b, and I can get it by doing a squared plus b squared equals c squared. Should be nice and easy. We know that xa is x, which is 3, and c is 5. So we get b is 14, or 4. B is 4. Once I get that, then I can do the adjacent is 4 over the hypotenuse is 5. And I can plug in 4/5 in for cosine of theta. So 4/5 times 3 equals 1/5 dx dt. I got rid of the 5's in the denominators. Both sides of a denominator 5, you can cancel it out. 4 times 3 is 12. All right, next one. This is a really great question. Like, this is a super great question for making sure that graphically you know what, f prime, f double prime being negative or positive would indicate. So when f of x is negative, that means that our graph needs to lie below the axis. So if I just look at A, B, C, D, and E, I can cross out E immediately. It's above the axis. Okay, I'll answer your question in 1 minute, Nayeli, after I finish this one. But really good question. Then f prime of x being negative. So f prime of x being negative means that f needed to be decreasing. So I'm just going to look at these. A, I have an increasing part. C, I have an increasing part. So now I'm between B and D. And then f double prime being negative would mean that f is concave down. So the entire time we need to be concave down. B is concave down the whole time. But on C, it switches. We switch from kind of concave down at the start to concave up over there. So we don't choose D. So this is kind of process of elimination, honestly. And we get B. So Nayeli asked about this question is, in this triangle, how did we know that 5 was a constant? And that's a really good question. Sometimes they're going to just have a situation where it has to be constant, right? Like the classic example is the ladder coming down the wall, right? I have some wall here, and I have a ladder, right? Well, as the ladder falls, can it get any bigger, any smaller? No, it can't. It just has to be the same length the whole time. Whereas other times I might have, one person here, and maybe this person, right? Let's draw him as a person. Making fun. Hands coming out of his torso or his hip, I guess. Kind of looks like a turtle person. He's going to the left, right? And maybe he started from some box. And there's another person, we'll make him a turtle as well. And he's going up. Right? And so what's going to happen is this distance is going to be changing. This distance is going to be changing. And the distance between them will also be changing. So in this case, there will be no constants, right? They're all changing. Well, in 23, they did not tell us any situation. They didn't give us a situation about, a person or anything like that. They just said in this triangle above, if theta increases at a constant rate of 3 radians per minute, at what rate is x increasing? So we know that x is increasing when x equals 3. The hint when x equals 3 and the fact that they told me x is increasing tells me that x is not a constant. And when I look on my triangle, they wrote this as x. They didn't write it as 3, right? They could have written it as 3, but they didn't. The reason they wrote it as x is it's changing. Now, they didn't even mention the hypotenuse, but they marked it as 5. Whenever they actually fill in a number here, if they put a number into the picture, that's always going to be a constant. Okay? So the fact that I see a number in my picture, I know it's constant. I see x in the picture, I know that's something that's going to be changing. And if you remember back to the related rates chapter, it's really, really important to know our constants because you can plug them into the formula before you take the derivative. Yeah, so if 5 was in the same place as B, I like that. How would this question change? That's a good question. So let me actually go ahead and add a blank page just so I have a little bit more room. So this question would be very, very similar. And I like that thought of what would have happened if they had done everything the same way, but now 5 was here. And we can do this really, really quickly without sidetracking us too much, is they put the 5 here, and then they put the x here. So they still said, when x equals 3, and they still said maybe d theta dt equals, I think it was 3 as well, right? Yeah. So in this case, what would change is, now here's theta, and I want a formula that's going to use x, which is opposite, and 5, which is adjacent. So what's going to change is, before, we started off with sine, because we had opposite and hypotenuse. So O and H makes so in SOHCAHTOA, right? We're thinking like SOHCAHTOA. So O and A, that matches with tangent. So our givens are the same. D theta dt equals 3. X equals 3. Our formula that we start with, though, is now tangent theta equals opposite x over adjacent 5. So then when I take this derivative with respect to time, the derivative tangent is secant squared theta times d theta dt equals, now you can do quotient rule here, like low d high minus high d low over low squared, but I like to kind of just treat it as 1/5 x. So the derivative of 1/5 is 1/5 times dx dt. Now, I don't have secant squared. I do have d theta dt, and I want to solve for it. We're trying to find dx dt. That's what the question asked me to find. So I need to figure out what secant squared is. Secant matches up with cosine. So I know cosine theta is adjacent over hypotenuse. Well, I know adjacent is 5, but I don't know hypotenuse. So to get that hypotenuse, I'm going to do an a squared, x squared, plus b squared equals c squared. Now, x squared is 3, so I can plug that in. That's 9 plus 25 would be 34. And then radical each side. So c is equal to the square root of 34, which would make cosine 5 over radical 34. Now, I didn't want cosine, I wanted secant squared. So if cosine of theta is 5 over rad 34, well then secant theta is just that flipped. So secant theta would be rad 34 over 5, and secant squared theta would be square both sides, square root of 34 squared, those cancel to 34, and 5 squared is 25. So this would be 34 over 25. So I'm going to multiply both sides by 5 to get rid of this denominator, to isolate for dx dt. That cancels down to 5. So I get 34 times 3 over 5 equals dx dt. 33 times 3 is 99, so this would be 102 fifths. And my units are, whatever they gave me, inches per minute. Or they just said in units per minute. So the units in this case are just units per minute. That's dx dt. All right, so I like that question. There is another one of those SOHCAHTOA kind of sine, cosine, tangent questions later on in the FRQ. And that one's actually a lot harder because in that one there are no constants. So you have to do quotient rule, and it's a little bit harder because of the no. Actually, it's probably quite a bit harder because of the no constants. This one I like. We've done a lot of concave down, but I like this one because of the solving with an e to the x. And I like to think about problems where we solve with e to the x because I don't think we did a whole lot of that last year in Math 3. especially with the quarantine and everything. So I like these types. So anytime I see concave down, we start off by setting f double prime to 0, right? Then we're going to make a number line, and we want where the number line gives us a negative value for f double prime. So first we're going to start off by taking the derivative. This is product rule. We have two x's. Derivative 2x is 2. Leave e to the x alone. Then plus, we're going to take 2x, leave it alone, and the derivative e to the x is itself e to the x. Now I'm going to take the derivative of that for the second derivative. The derivative of 2e to the x is just 2e to the x. Then plus, now this one is going to be a product rule. So I'm going to take the derivative of 2, leave it alone. Sorry, take the derivative of 2, and then leave e to the x alone. Then plus, now I'm going to leave 2x alone, and the derivative of e to the x is e to the x. So I'm going to set that to 0. Now, when I try to set this to 0, right, I want to simplify as much as I can and factor if I need to. But what I notice is this term, the first term is 2e to the x, and this is 2e to the x. Think of this as, I know 2e to the x is weird, but just think if I had 2 box plus 2 box, what is that? It's 4 box. So this is 4e to the x, and then this just stayed the same. Right, so now, what do I have? Whenever I'm solving equal to 0, I always want to see if I can factor. Factoring will always help us start off. If we're not sure what to do, factor. So in both of those terms, I have a 2e to the x. Both sides have 2e to the x. So I'm going to factor out 2e to the x, and then I'm left with 2 plus x. So when I set 2e to the x equal to 0, I can divide by 2, I get e to the x equals 0. In order to cancel out e, I take the ln of both sides. And the ln of 0 does not exist, so I get no solution. This is actually pretty key. Is e to the x equals 0, or really anything to the x equals 0, will always have no solution. It never ever happens, right? And in fact, we need to know that e to the x, or a number to the x, is always positive, right? And you want to remember this graph if you can, from Math 1 actually, is the exponential graph. Right? It has a horizontal asymptote at 0, and it crosses at 0, 1. Right? And that makes sense because e to the 0 is 1. So the y value at 0 should be 1. And our graph can never ever go negative, right? Our graph never goes negative. The y asymptote, horizontal asymptote, is y equals 0. So that's important to remember, is e to anything is always positive. That's something you just kind of have to know. Then when we set the 2 plus x to 0, we get x equals negative 2. So my only possible inflection point, right, that's a possible inflection point, is at negative 2. Then what we're going to do is we're going to go ahead and plug in a number smaller than negative 2. Let's pick negative 3. 2e to the negative 3 is positive. Even though it has an e to the negative 3, it's still positive, right? 2e to the negative 3 is just 2 over e cubed. It's a decimal, but it is positive. Then negative 3 plus 2, right? Negative 3 plus 2 will end up being negative. Okay, so negative 3 plus 2 is negative. So this first part was negative. Then if I plug in 0, e to the 0 is 1, it's positive. 2 plus 0 is positive. So this part is positive. And the question asks, where is this concave down? It's going to be that section from negative infinity to negative 2, or just x is less than negative 2. Next up, the radius of a circle is increasing at a constant rate of 0.2 meters per second. This says calculator. Oh, I think I skipped one. I did. Let's go 28. There we go. Let g be a twice differentiable function such that g prime of x is greater than 0. As soon as I see that, we're thinking g is increasing. And g double prime of x is greater than 0, meaning g prime is increasing, or even g is concave up. And then they give us g of 4 is 12, g of 5 is 18, and what is a possible value for g of 6? So anytime they give me points, one possibility is to graph them, to plot them. 1, 2, 3, 4, and then up. I'll count by 6s. 6, 12, just so I can make this easier to graph. And then at g of 5, we're at 18. So I could even try graphing this. Right, so if I'm counting by 6s, the next one is 24. Now, if it says that G prime is greater than 0, we're increasing, so I know this graph needs to be increasing. But then it also says G double prime is greater than 0, it needs to be increasing and concave up, right? It needs to be going concave up. Well, if you look at it going concave up, you can see it's going to really increase rapidly, right? And what concave up means is that G prime is increasing. So this, went up by 6. Concave up means that the next one needs to jump by more than 6. Now on a graph, we can kind of see it, but it's a little hard to tell. I find this way easier to do on a table. So what I did is I made a table, and 4 matches with 12, 5 matches with 18. So from 12 to 18, we increased by 6. And then we don't know what we're going to increase the next time. But we do know because G is increasing, G prime is greater than 0, we know that we need to increase by something. And because G double prime, right, we know that this also needs to be a positive number, right? From 6 to whatever else, this needs to be positive, the change. Which means this number here needs to be bigger than 6. So 7, 8, 9, 10, anything like that. Well, when I look at these values, A would have decreased. 18 to 15 decreases. B would have stayed constant. C only went up by 3. We want to go up by more than 6. 24 goes up by 6, but we want to go up by more than 6. 27 is the only one that goes up by more than 6. All right, so 78, it says calculator question. I honestly did this one without a calculator. But, a calculator I think would help you be a little more comfortable with the decimals. So they give us the radius of a circle, and then we see the word increasing, and we also see the word rate, and we also see these units. All 3 of those should tell me that this matches with dr dt. So dr dt is 0.2. And then what is the rate of increase of the area? So they want dA dt. That's what they want. The increase, right? Rate, increase, area. That's dA dt. At the instant when the circumference is 20 pi. So circumference is 20 pi. I like to immediately change this to 2 pi r. So 2 pi r is 20 pi. The pi's cancel out. So really what they gave us is they didn't give us the circumference. If I divide by 2, they gave us the radius. So I'm going to even add this to my givens. That's what they gave us. Now we want the area. So I started off with just area equals pi r squared. But we want the rate of the change of the area. So we're going to do d dt to both sides. And that gives us dA dt equals, derivative of pi r squared is 2 pi r times dr dt because they're different variables. We know r is 10. We know dr dt is 0.2. 2 times 10 is 20. 20 times 0.2 is 40. Move the decimal place over, 4. And then the pi is still there, so our answer is 4 pi, which is choice C. Next one is actually very similar to our previous calculator question, but instead of asking for the number of inflection points, they just say what is the x-coordinate of the inflection point. And again, they gave me f prime of x. This time they do not have an interval, like a window, to change to. So we're just going to probably go to the standard, right? If we don't have one, I always recommend going to the standard. So I'm going to first go to menu, actions. Actually, I'm not going to delete all. And the reason I'm not going to delete all is I'm going to be kind of smart is I want to graph f double prime again, right? Because they gave me f prime, right? That's what we were given f prime. But to graph an inflection point, I want to graph f double prime. So I'm going to need to do the derivative, right? I need to graph the derivative of that. And on my graph, the last one we just did was also a derivative. So I'm actually going to just hit tab and just take out the inside because that's just a little bit lazier, right? And I'm always trying to be as lazy or as efficient as I can. And we have square root of x over 1 plus x cubed. That's the nice thing about being a math teacher, right? If you're lazy, you can just call yourself efficient. And you say, no, I'm not lazy, I'm efficient. Okay, so an inflection point is where our graph passes the axis. I see it happens right there. I'm going to go to menu, analyze graph, and 0. And we have to the left and to the right, 0.473, 0.473. So, oops. So that's choice B. All right, Nayeli, you asked about 10 or 10 pi. I think that's talking about this one. So it's just 10. The reason it's just 10 is, I'll write it over here on the side. We had circumference was equal to 20 pi. I think you're asking about r. The formula for circumference is 2 pi r equals 20 pi. So what's going to happen is the pi's are going to cancel out. So I like to just do that. But I guess hypothetically, if you didn't cancel out the pi's, you could have just divided by whatever's not r, divide by 2 pi, and divide by 2 pi. So the pi's cancel, and then 20 over 2 is 10. So that's why the radius is 10. Yeah, thank you, Jimena, as well, for mentioning that in the comments, that, yeah, the pi's canceled. Okay. 90 is similar to this question 28. They're kind of similar. So we have for all x in this interval from 2 to 5, we have a positive first derivative and a negative second derivative. I think we've also had a couple of these on tests before. So when we have a positive first derivative, we know that f prime is positive and f is increasing, right? We know that f is increasing. And then we have a negative second derivative. I'm going to do this in the other color. I'm going to do this in blue. So the negative second derivative means that, right, f double prime is negative, which would mean that f is concave down, but that also means that f prime is decreasing. And so what I like to kind of do is look at, for the first derivative, it's positive. The first derivative is going to be my change. So this adds by 2. This adds by 3. This adds by 4. Okay, that's just my first derivative. It needs to be positive. And then I'm going to go to the next one. Adds by 4. Adds by 3. Adds by 2. Go to the next one. As soon as I see subtract by 4, I can immediately get rid of this one, because I need a positive first derivative, which means f was increasing. Same thing here. It decreased by 2, I can get rid of it. Same thing here. It decreased by 3, I can get rid of it. So I'm down to either A or B. Now I want to look at what would a negative second derivative mean. That's the change of the change. Well, from 2 to 3, we add by 1, but I want a negative. So I can get rid of A. And look at B. From 4 to 3, we did decrease by 1. We did decrease by 1. So that guy works. Three, any question with a farmer and fence, this is like the most classic optimization question. Okay, there's either going to be a wall or a river, and he's trying to build some kind of a fence, maybe to house his cows or just, for whatever reason, right? So you can always draw this picture, right? So here's my river, and this side does not get a fence. So he doesn't need that third side. So we're going to call this X, but then we only need one Y because the other side is our river. So they always give you some amounting of fence, right? 100 feet of fence, 500 feet of fence, whatever he has a fence. That is always going to be our perimeter. And so the perimeter around this, we add up all the sides. X plus Y plus another X makes 2X plus Y equal to 100. This is my support equation. It's not what I'm trying to optimize or maximize or minimize. They say, what is the largest area? So we want to optimize the area. The formula for the area of a rectangle, which a fence would form a rectangle, is X times Y. It doesn't matter that it's missing this third side, fourth side really. That side is there, it's part of the river. So that side is length Y, we just don't need that to build the fence. So the area is X times Y. I want this to have one variable. That's the key for optimization. I need that to have one variable. So what I'm going to use is I'm going to use this supporting equation, and I can either solve for X or for Y. This one looks easier to solve for Y. So I'm going to subtract 2X to both sides, and then we get 100 minus 2X. We're going to plug that in to this equation over here, and that gives me area equals X times 100 minus 2X. Go ahead and distribute. That's area equals 100X minus 2X squared. Now we're ready. This is ready to optimize. The way we optimize is we always take the derivative, equal it to 0, right? So if they say largest area, that means I want to take the derivative of the area, set it to 0. So find the maximum area. So a prime would be derivative of 100x is 100 minus derivative of 2x squared, 4x. Add the 4x over, divide by 4, we get x equals 25. Now, they didn't ask for x, they asked for what is the largest area. So I need to go back and I need to basically solve for this area. In order to solve for area, I need x and y. I now have x, I need to get y. How am I going to get that? Plug it back in up here. 100 minus 2 times 25. I did that right there. We get 50. Now that I have both 25 and 50, I plug both of those into my area formula, which was x times y. And 25 times 50, 25 times 5 is 125. Add the 0, 1250. Next up, they give us a graph of just y equals f of x. Not f prime, not f double prime, but f of x. They say, how many inflection points does this graph have? So if it was f double prime, this is not. But if it was f double prime, we'd have 1, 2. It's not that, though. It's just f. So inflection points are when f changes concavity. So this graph starts concave up, and it switches somewhere around here to concave down. That's my first point. Then right around here, it switches back to U-shaped concave up. That's my second point. Then right about here, it switches to concave down again. So somewhere in here, that's my third point. And it remains concave down. So I have 3 inflection points. Now, I added, just for us to think about, this wasn't the AP question, but how many inflection points would this graph have if it was the graph of f prime of x? So I want you to kind of ignore everything we just did. And now in your head, change this graph to be the graph of f prime of x. Well, f prime, when f prime changes between increasing and decreasing, that's when we have inflection points, right? F double prime would change between positive and negative, which would mean we'd have inflection points. Right, f is changing concavity. When we change between increasing and decreasing, those are just maxes or mins, right? Relative maximums, relative minimums. So if this had been the graph of f prime, let me kind of erase all of this. The red isn't going to erase, unfortunately. But this graph is basically decreasing. It continues to decrease. It kind of pauses here. That would be a possible inflection point. But it's not an inflection point because it continues, the graph continues to decrease. Then here it bottoms out, right? I get this horizontal tangent. We get a relative minimum. And this is my first inflection point, because then the graph changes to increasing. So now my graph is increasing, increasing, increasing. Then it reaches this maximum value, which again would be another inflection point, and we change to decreasing. So this would have been 2. We would have had 2 inflection points if it had been the graph of f prime. This next one, if y equals ln of x squared plus y squared, what is the value of dy dx? As soon as I see dy dx and I have y's embedded in my equation, that's implicit. Now this one can be a little hard for people because a lot of people forget about that first y. But it's y equals ln of x squared plus y squared. I've seen a lot of students ignore that first y. You can't. Right? So this is d dx, d dx. So we get dy dx on the left. This is ln of something. So the derivative of ln is 1 over that something. So 1 over x squared plus y squared. And times, I'm going to put this in parentheses. Derivative of x squared is 2x. Plus the derivative of y squared is 2y dy dx. I need to do that implicit. Then we can move this to the top. I like to do that. And as I did that, I also plugged in x as 1 and y as 0. So we get this 2x becomes 2 times 1 on top, plus 2y is 2 times 0 times dy dx. So this entire part goes away over x squared 1 squared plus 0 squared. That's equal to dy dx. We get dy dx equals 2 over 1, or just 2 is our answer. 17 is another implicit, but this time second derivative. Second derivative is a little bit harder. There's just an extra step. So the derivative is really easy here. The hard part is the second derivative. So derivative x squared 2x plus derivative y squared 2y dy dx equals derivative 25, 0. Subtract 2x and then divide by 2y. We get dy dx equals negative 2x over 2y. I did that all in one step. And we can cancel out the 2's. So we get dy dx equals negative x over y. But we didn't want the first derivative, we wanted the second derivative. So we're going to come up here and take the second derivative. So the way we do that is this is quotient rule. Low is y. I'm not putting a dy dx because I left it alone. It's just low. D high is the derivative negative x is negative 1. Again, no dy dx because it's the derivative of the x part. Then minus high, negative x, and d low is dy dx, 1 dy dx, all over low squared. So as soon as I get this line here, that is d squared y dx squared. I'm going to immediately plug this in because that's what they wanted us to do. I wrote it kind of this fancy way, d squared y dx squared at 4, 3. You don't need to write it that way. What you need to do is you need to plug in y as 3 and x is as 4. 4. So we get y is 3 times negative 1 minus negative x becomes negative 4. Now I don't know what dy dx is, but I need to plug this in too. So I need to plug in, for x I need to plug in 4. For y I need to plug in 3. And for dy dx I need to plug something in. Right? Well, what is dy dx? It was negative x over y. So that's negative 4 over 3. So for the dy dx, right, we plugged in negative 4 over 3. And all over y squared over 3 squared. When we do this, we get negative 3 times negative 1 is negative 3. Minus, now this is 1, 2, 3 negatives. So negative times negative stays minus, right? You could have made these two positive, but then I have 4 times negative 4 turns negative 16 over 3. So I multiplied all 3 of my terms by that 3 to get rid of that denominator. That gives me 9, negative 9, minus 16. It's negative 25 over 27, choice A. All right, next we have this graph, and they tell us it's the graph of the derivative. That's the most common one to give the graph of the derivative. And we're asked to find an equation to the tangent line. This is actually pretty common on FRQ. It's less common on multiple choice, but they do ask it from time to time as evidenced here. So as soon as I see equation of the tangent line, my first thought needs to be x1, y1, and m. They say at 3, 5. So they gave me the x1 and they gave me the y1. Well, how do I get the m? The m is just the slope or the derivative, right? So this is f prime of 3 because that's the x that we have. So I'm going to look on the chart for f prime, and the y value there is 2. So f prime of 3 would be 2. Then I just do y minus y1 equals m times x minus x1, and it's literally written in that form, choice C. Very, very simple question. But you do need to understand that m matches up with the y value for the derivative graph. Right, how many points of inflection does the graph of f have? This is still for this question, right? It said refer to this question for 7 to 9. So how many points of inflection? Well, this is the graph again of f prime. So we need to know that inflection points on f prime are when f prime changes between increasing and decreasing, which are also our relative maxes and mins. So up here, I counted 1, 2, 3, 4, 5 relative max, six relative max and mins, where the graph changes, increasing to decreasing, back to increasing, and keep going, right? But we had 6 of those. And finally, I think this is the last multiple choice. Yeah, last multiple choice. The graph of y equals negative 5 over x minus 2 is concave down for all values such that, so concave down is that same thing we said before, y double prime, set it equal to 0, make a number line. Where do we see negatives? So that's our process. Now, this derivative is a little tricky, and technically, if you really, really want to, you can do quotient rule. So you could do a whole low d high minus high d low all over low squared. But whenever I personally notice either the numerator or the denominator. If one of those does not have an x in it, then I don't do quotient rule personally, because it's just faster to do it other ways. So for example, if I had, I'm going to kind of just write this down here. If I had y equals 3 over x, right, I could do quotient rule, but I find it better to do reverse power rule. Put a 1 there, go up, 1 times 3 is 3, turn it negative, over x squared. If instead I had y equals x over 4, I find it faster to kind of treat this as 1/4 x, right? You can even rewrite it that way, 1/4 x. Well, what's the derivative of 2x? 2. The derivative of 1/4 x is 1/4. So this is similar to that, where I have negative 5 over x, but this is just a box, right? So this is chain rule. So the derivative of like y equals negative 5 over box, well, y prime would be, this is to the first power, multiply up, 1 times negative 5 is negative 5, change the sign, 5 over box squared times the derivative of the box. Well, this derivative of the box is really easy because the derivative of x minus 2 is 1. So we're going to do that reverse power rule. I'm going to multiply up. 1 times negative 5 is positive 5. And then over x minus 2 squared. And then this times 1 is just because that's times the derivative inside. Now it goes away, like we don't really need to write times 1, but I'm just showing it. Now I'm going to do reverse power rule again. For the second derivative, 2, multiply it up. 2 times 5 is 10, but now it's negative 10. Then over add 1, x minus 2 cubed, and then again times 1, because that's the derivative inside. But we don't really need to worry about it. So our y double prime is negative 10 over x minus 2 cubed. So I wrote negative 10 over x minus 2 cubed. And we're going to set this equal to 0, but because it's a fraction, we need to also remember dne. So it's either equal to 0 or dne. To do the 0 case, I'd set negative 10 to 0. Negative 10 is not 0, right? Those are not the same. So because that's false, there's no solution for the 0 case. Then I set the bottom to 0 for the dne case. X minus 2 cubed equals to 0. That gives me x equals 2. And so we're going to plot that on our number line. And when we plug in 0, where are we plugging this in, by the way? We're plugging it into f double prime. So when I plug in 0, negative 10 over 0 minus 2, right? Like negative 10 over negative 2 cubed. That's a negative over a negative, which turns positive. Then if I plug in 3, we get negative 10 over, say like 3 minus 2, which is 1 cubed, which is negative over a positive, which is negative. So that's where we're concave down when x is greater than 2. Moving on to the FRQs, let's do these as quickly as I can because this video is already creeping up on an hour. So consider the graph given by this implicit, right? We know it's implicit because we see dy dx with all these x's and y's. We have x's and y's. So show that dy dx. They just want to show step by step as much as we can. So ddx. It's not a rate. ddx. ddx. The derivative of x y squared. This is product rule. Derivative of the first. 1. Leave y squared alone. Plus leave x alone. Derivative of y squared is 2y dy dx. Now this next product rule is a little hard because of the negative. Okay, when you have that negative, it needs to be negative in both terms. Just remember that. When you have a negative for product rule, both terms need to be negative. So the derivative of negative x cubed is negative 3x squared. Then I leave y alone. Then plus in parentheses, I'm going to leave negative x cubed. Then the derivative of y is dy dx. I want to isolate for dy dx. So I'm going to leave the two terms with dy dx on the left and move these other two terms to the right. 2xy dy dx minus x cubed dy dx equals negative y squared plus 3x squared y. Then we'll divide out the other terms. We get dy dx equals 3x squared y minus y squared over 2xy minus x cubed. You could even put a check mark because you're checking that it is the same as that. Right? You want it in the same order too. If you had any of these, like here I had negative y squared first. So I just moved this first because that way it would match with what they wrote. B, find all points whose x-coordinate is 1. So find all points whose x-coordinate is 1 and write an equation for the tangent line for each of these. So we're going to start off with we're going to just start off with an x1, a y1, and an m, right? So I'm going to kind of do this up here just so you can see what we'd start with. An x1, a y1, and an m. Now, I want an x-coordinate of 1. So where do I go first? First, I plug into the original. Okay, so that was over here, right? X, y squared minus x cubed y equals 6. So for x, I plug in 1. That gives us y squared minus y equals 6. If I have a y squared and a y, I need to set it to 0 and factor. So y squared minus y minus 6 equals 0. Anytime you're not sure how to solve something, think about factoring. It's probably right. Then this becomes y minus 3 and y plus 2. That gives me y equals 3 and negative 2. So now, if I get 2 answers, and it did say find all points, that means I have 2 tangent lines. So I have one with 1 and 3. Then I have another one with 1 and, was it 2 or negative 2? 1 and negative 2. So I have 2 x1, y1s, and m's. And they will have different m's. That's okay. They will have different m's. So how do I get the m? Well, I need to plug basically both of these 1 and 3. Now I plug them into the derivative. Plug in 1 and negative 2 into the derivative. So I showed that down here, right? For 1 and 3, I did that right here. Anywhere I see an x in the derivative, I plug in 1. So 3 times 1 squared times. And then anywhere I see a y in the derivative, I plug in 3. Minus 3 squared over 2 times 1 times 3 minus x cubed 1 cubed. This gives 9 minus 9 on top. Over 6 minus 1, that's 0, right? 0 over 5 is 0. When 0 is on top, it's 0. So for this first x1, y1, and m, I'm going to put my m as 0. Now that I have all 3, I can write an equation. Y minus y1 equals 0 times x minus x1. 0 goes all the way away, so I can just add 3 over y equals 3 is a good answer. Now, could I have left this up here? Absolutely, like this could be an answer. But this is really easy if you want to do it. Then I do the same process over here on the right, right? The same process for 1 and negative 2. I'm plugging in to dy dx. And anywhere I see an x, I'm plugging in 1. This time, anywhere I see a y, I'm plugging in negative 2. So we do all that work. We get negative 6 minus 4 over negative 4 minus 1. Simplifies to negative 10 over negative 5, which is 2. So this slope is 2. So this is y minus y1 equals m times x minus x1. I just changed the negative to positive, and that's my answer. And then C, we have find the x-coordinate of each point where the tangent line is vertical. Tangent line is vertical. So if I ever see something like this, I could see tangent line horizontal, or I could see tangent line vertical. For tangent line horizontal, I know that m is 0, which on these implicit ones, dy dx, equals, I'm going to call this like p of x, the numerator, over q of x, the denominator. We're going to set this to 0, but really it's just the top needs to equal 0. For a vertical tangent, that's when I have an undefined slope. So I have dy dx equals p of x over q of x. This time it's going to equal to undefined, but what we can do is we can set the denominator to 0. That will give us undefined. So that's this case. So what we want to do is we want to write out our x1, our y1, and our m, as I did here. And then for the undefined, what that means is the denominator is 0. Well, coming back up here, the denominator is 2xy minus x cubed. We're going to set that equal to 0. Now, this looks extremely intimidating to solve. I'm like, how the heck am I going to solve 2xy minus x cubed equal to 0? Well, realize, hey, I have 2 variables. If I have 2 variables, I need a second equation. Okay? And that second equation on these implicits will always be your very original equation. So that's what I did first, is I just wrote those 2. Now again, this is still really, really intimidating. When I look at it, I'm like, how the heck am I going to solve either one of these? And The right one, I literally cannot solve. The reason I cannot solve is it's set to 6. So I can't solve it right now. But the left one is set to 0. Whenever it's set to 0, I've said this a few times tonight, is try factoring. So let's see, what can I factor out? I have an x in both of these. So I could factor out an x. X times 2y minus x squared equals 0. This gives me x equals 0. Okay, I can work with that. This is a little harder, right? If I added x squared to both sides, 2y equals x squared. Divide by 2, y equals x squared over 2, or 1/2 x squared. Okay, it's not as nice, but I can work with it. We're going to take both of those, and now we're going to substitute them back into the original. So I started off with x equals 0. This is the x equals 0 work. 0 times y squared minus 0 cubed times y. But I got 0 equals 6, which kind of sucks, but that just means no solution, right? 0 is not 6, so I have no solution. So that didn't give me any answers. Then I'm going to plug in y equals 1/2 x squared, and the work for this kind of sucks, but it is doable. So x times, for y, 1/2 x squared squared, minus x cubed times just y, 1/2 x squared equals to 6. We're going to square everything. So this is x times 1/2 squared is 1/4, right? 1 squared over 2 squared is 4. And times x squared squared, right? When I have x squared squared, those multiply to x to the 4th. So that makes x times x to the 4th is x to the 5th. And it's 1/4 x to the 5th. I wrote that right there. Then minus x cubed times x squared gives another x to the 5th, but this time it's 1/2 x to the 5th equals 6. I absolutely hate fractions. So because I don't like fractions, I am going to multiply each denominator by 4. Okay, and then those cancel. And I get x to the 5th minus 2x to the 5th equals 24. X to the 5th minus 2x to the 5th is negative x to the 5th. Equals 24. Divide out the negative sign. X to the 5th equals negative 24. And then 5th root them. That's a really weird one, right? Like x squared, we square root. X cubed, we cube root. X to the 5th, we 5th root. The answer is x equals 5th root of negative 24. Extremely difficult, extremely weird. And I come back up here, they just ask for the x coordinate. Now, on this question, here's the deal. It was a part A, a part B, a part C. The part C is kind of a weird one, but part A was actually really easy, and that's like a nice 2 to 3 points. And part B, I thought was, still medium, but not too bad. And part C was definitely tricky. Okay? But if you can get A and B, you're sitting in a really good spot to get a 3, 4, even a 5 on the AP exam. And then if you could have gotten some points here, like this line, I don't think is that bad. Okay, that line right there is not that bad because it's knowing that M is undefined, and this would have been 1 point. So at least I'm getting some partial credit. Okay. Johannes Kepler, love the name. And Nayeli is asking about, should we add, multiply or add the exponents? I'm not sure about which step you're talking about, Nayeli. So just kind of in general is if I have like x squared cubed, this is always multiplying. This would be x to the 6th. Right? So in our case, we had 1/2 x squared squared. This is multiplying exponents. 1 is to the 1, 2 is to the 1. Squared, x squared is to the 2. So I multiply 1 times 2, 1 times 2, and 2 times 2. So that's 1 squared over 2 squared times x. 2 times 2 is to the 4th. We multiply it. That's why I got 1/4 x to the 4th. Okay. There was an x in front, but we multiply. So whenever we're doing it that way, we multiply. Then give me 1 second because my tablet just disconnected. I got to get it back up. When we have like x cubed times x squared, that's when we add exponents. So let's get this going. Okay, hopefully I do have to close my streaming program. All right, perfect. So we should be back. So my tablet is just saying go a little bit quicker. Doesn't like being connected remotely this long. Okay, so again, long story short, right? X squared times x cubed, we multiply. If I had something like x squared times x cubed, that's where we add x to the fifth. So we actually had both of those here. Because in this first one, we're multiplying exponents. But then, once I've done that, I have x times that x to the fourth, right? I kind of wrote that in here. X times x to the fourth, that's where I add them. X to the first plus 4, like x1 plus 4 is x to the fifth, right? Actually, that was not right there, but up there in that line. And then, again, here I had x cubed times 1/2 x squared. So the cubed and the squared there add because I'm multiplying, right? So when I'm multiplying two different x's times each other, I add. When I have an exponent raised to another exponent, that's where I multiply. So this is the one I talked about earlier that I said is on the FRQ where I have no constants. So as I read this, I have ship A traveling due west. I think this was in one of our previous practice tests as well. So ship A is going to the west, north, east, southwest. It's going this way. And ship B is going north. That's going up. So what that means is we need to be careful with that, is that means that x is getting smaller, right? So like dx dt, right? Ship A is getting closer to the lighthouse. So this distance of x is going to be getting smaller. Whereas ship B is going up, it's getting further away from the lighthouse. So I know dy dt will be positive just looking at the picture. And that's a nice way for me to check my answer later. So as I read this, ship B is traveling due north at a speed of 10 kilometers per hour. Speed is not rate, but it is another kind of word for rate. So when I see speed, I know that's like a rate, and especially when I see kilometers per hour. So that 10, what they gave me with 10 is they gave me dy dt is equal to 10. And I know it's positive 10 because it's going up, it's going away from the lighthouse. Then x is our distance between A and the lighthouse. And that's kind of all they gave me at all. Oh, they did say ship A, I messed that up. Ship A is traveling at a speed, again, that's a rate, of 15 kilometers per hour. Again, that's my rate. So A is going to the west, so that's dx dt. Now, instead of positive, it's going to be negative 15. Again, the reason it's negative 15 is this distance is going to be shrinking. It's going to be getting smaller as my ship goes to the left. So A, one of the easiest questions you could ever get asked is just find the distance between ship A and ship B when x is 4 and y is 3. So if I draw in that triangle, they want this distance. We'd call it whatever we want. We'll call it C because it's a right triangle. When x is 4 and y is 3. You actually don't need to show any work on this. If you literally just said 5 kilometers with no work, you would get full credit. Because the AP graders know that you can memorize the common triangles, right? The 3, 4, 5 triangle, the 5, 12, 13 triangle, the 7, 24, 25 triangle. So if I see 3, and I see 4 as my two legs, we can just say, hey, distance is 5. Now, if you wanted to show a squared plus b squared equals c squared, you totally could. And next, find the rate of change. So I want the rate of change of the distance between the two ships. I called this c, so we want dc dt. That's what we want. When x is 4 and y is 3. So this is a related rate. So I'm going to kind of set up my 3 sections. We're given dx dt is negative 15, dy dt is 10, x is 4, y is 3. So it gives me x squared plus y squared equals c squared. I can't plug anything in. because none of those are constant, right? So if it was one of the latter questions, then I could have set, c to 5 and plugged it in right here. But because it's not constant, right, all three of these are changing, I need to leave it as x squared plus y squared equals c squared. How do I know they're all three changing? Just kind of imagine it. As this ship comes closer and this ship gets further away, this overall distance will be changing because it's not something that needs to be locked in place like a ladder. So now, let's see. When we take the derivative of x squared is 2x dx dt. Derivative of y squared is 2y dy dt. Derivative of c squared is 2c dc dt. I can cancel out all the 2's. And I just plug everything in. X is 4, dx dt is negative 15, y is 3, dy dt is 10, and c is 5. I want to solve for dc dt. I do the math, negative 60 plus 30, negative 30 divided by 5, negative 6 kilometers per hour. Okay. And then finally, let theta be the angle shown above. So before I start this one, I'm going to say the same thing as what I said before. A and B here, these are the ones that you want to get the most points on. Okay, like these are the ones that really matter. The curve is such that if you got all of the A's and all of the B's correct, you would easily pass the AP test, easily. Now, C's are very nice to get right, but they're always going to be, or almost always going to be a little bit more challenging. So let theta be the angle shown in the figure, right? I kind of covered it up when I drew all this stuff in, but theta is right there. And find the rate of change of theta in radians per hour when x is 4 and y is 3. Now, I can either choose so, ka, or toa, any of those three. It doesn't matter which one I choose. However, for me, right, and the reason I can choose any is I know x, I know y, and I know c, and I know that all three are changing. So it's not going to matter which one I choose. If c was a constant, and if I only knew about x, then I would want to choose cosine, right? If x was a constant, and I only knew about y, well, then I would want to choose tangent. But in this case, all three are changing, so I can pick any one of them, so, ka, or toa. So the next choice would be, if any of them are not whole numbers, like if any of them are radicals, I'd probably avoid that one. But it's a 3, 4, 5 triangle, so I can literally choose any of them. So in that case, I always kind of default to sine, because sine is just the easiest derivative. Derivative of sine is cosine. So I chose sine. So I just said sine theta, right? What is sine theta? Sine theta is opposite over hypotenuse. So in this case, opposite side is y over c. So you get sine theta equals y over c. Now, if you do cosine or if you do tangent, you're going to get the exact same answer. It just is going to work out a little bit differently. So I'm going to take I start off by taking the derivative of both sides. The derivative of sine theta is cosine theta times d theta dt. We have to do that related rate. And this next part is a little bit harder. Y over c. Because neither one of those are constants, we have to do quotient rule. So low d high, leave the low alone. C, derivative the top, derivative y is dy dt, right? Because it's with respect to time. Then minus, leave y alone. The derivative of c is 1 dc dt because it's with respect to time, all over low squared over c squared. Now I can plug in for c, 5. I can plug in for dy dt, 10. I can plug in for y, 3. I can plug in for dc dt, negative 6, right? That's what I got up here. Then I can plug in for c, 5. I cannot plug in for cosine theta yet. And I don't want to plug in for d theta dt because that's what I'm trying to solve for. So in order to get cosine theta, we need to think, okay, what is cosine theta? It's the adjacent over the hypotenuse. My adjacent side is x, over the hypotenuse is c. X is 4, c is 5. So we can plug in 4/5. And now from there, it's just a bunch of math and simplifying. You actually don't need to simplify it. You left it as 68 over 25 times 5 over 4. That's fine. I went ahead and I simplified it to 17 over 5. But, you did not need to fully simplify that. We cannot do inverse power rule here, Nayeli, because it's not, like, before we had a constant, like we had 5 over x. That would be inverse power rule because the top is a constant. But in our case, we have y over c. This c is not a constant. Okay, that's not the constant c. That's c as in a squared plus b squared equals c squared. It's a side. Both of these are variables. So when they're both variables, you need to do quotient rule. Right? The reason I could have done reverse power rule here is because the top is not a variable. The top is 5. So I warned you about this. I said it's going to be a little bit harder because they're both variables. And again, if you got A right, you got B right, you're passing the AP exam. You get C right, that's where you kind of take yourself to that track for a 5. This one, I think we could get A, B, and C right pretty easily. We're given a graph of the derivative. And where does x have a horizontal tangent? We've done this a ton of times. Horizontal tangent when f prime is equal to 0. So 1, 2, 3, 4 times. We're just going to say f has a horizontal tangent at all 4 of those, -7, -1, 4, and 8, because f prime of x equals 0 at those values. For what values does f have a relative maximum? Okay, relative maximum is when f prime changes from positive to negative. That happened at -1 and at positive 8. So f has a relative maximum at x equals -1 and 8 because f prime changes from positive to negative at those values. And this is the little bit new part from this chapter, whereas f concave down. Well, f concave down, which graph do we have? We have the f prime graph. That matches up with f prime decreasing. You just need to memorize that, right? F prime increasing is f is concave up, and f prime decreasing, f is concave down. It just has to get memorized. So because I have this f prime graph, f concave down matches up with when f prime is decreasing. We can grab these inflection points by looking at the maximums and the mins. Those are my inflection points. So f is going to be decreasing in between those two and after that one. So that's from -3 to 2, and then also from 6, not to infinity, but to 10, because this ends at 10. So this would be f is concave down for -3 to 2, union 6 to 10, because f prime is decreasing for those angles. Yeah, Jimena, you can never, ever, ever use L'Hopital's except for with limits. So anytime I have, like, say, y equals whatever it is, let's just make something up, like x squared minus 3 sine of x divided by 2x. Okay, if I want to find this derivative, we have to do quotient rule. Okay, in order to find a derivative, we have to do quotient rule. Okay, because quotient rule is what the derivative is. A L'Hopital's rule is not that. L'Hopital's rule is totally separate. L'Hopital's rule is like the limit as x approaches 2, like x squared minus 4 over x minus 2. Okay, and what happens is we get this 0 over 0, this whole. And what L'Hopital discovered, right, was that when I get 0 over 0, basically this is the limit as x approaches 2. He called this actually f of x. And he called this g of x. And he discovered that this limit will basically be, if the limit as x approaches 2 of f of x is equal to 0, right? The limit of the top is 0. And the limit as x approaches 2 of the bottom is 0. He discovered that if that was true, right, we get this 0 over 0, that then this limit would be the same limit as the limit as x approaches 2 of f prime of x over g prime of x. And that's kind of what L'Hopital discovered. But this is absolutely not quotient rule. Okay? So this is not, right, when I do these separately, it is not the derivative of like the entire top. Right? If I wanted to do the derivative of this, I would do quotient rule, right? Low, 1, d high, x squared minus 4, minus high, x squared minus 4, d low, low, d high, totally did that wrong. Low would be x minus 2. D high would be 2x. Minus high, x squared minus 4. D low, 1. All over low squared. This would be quotient rule. So this would be the derivative of what I have circled. But L'Hopital's rule is to find the limit, totally separate, which would be the limit as x approaches 2 of 2x over 1, which is 4. So those are totally separate cases. I love the question because it's something that I think a lot of students maybe like want to do or want to start like thinking about and trying to figure out is, can I do L'Hopital's rule? When can I do L'Hopital's rule? When can I do quotient rule? But quotient rule is basically exclusively for finding the derivative, and L'Hopital's rule is exclusively for finding a limit. Okay. So next one, I think we got, what, 3 left? Yeah, 3 left. Okay, and the last 2 are a lot quicker. So this is our last long one. So consider this curve given by x squared plus 4y squared equals 7 plus 3xy. Immediately, that kind of looks like implicit. And when we see part A, it's definitely implicit. So show that. So derivative x squared 2x, derivative 4y squared 8y dy dx. And then this part is the product rule. Derivative 3x is 3. And then we're going to leave y alone. Then plus, leave 3x alone, times dy dx. So anything with dy dx, I'm going to move to the left side. Anything without, I'm going to move to the right side. Then I'm going to divide by the 8y minus 3x, and that gives me this. I'm going to kind of put a check mark to show that I'm looking at it. Okay, part B, show that there's a point P with x coordinate 3, at which the line tangent to the curve at P is horizontal. So if I see a horizontal tangent, I'm thinking that m is 0, which I set the top to 0. So if I set the top of this 3y minus 2x to 0, get 3y equals 2x, that's y equals 2/3 x. Then this is still not solved, so I always need to set this, plug this back into the original equation. Right? This has 2 variables. If I have 2 variables, I need 2 equations. So my other equation on implicit is always my original. So anywhere I see a y, I'm going to plug in 2/3. These are kind of tricky, but it's the same process every time. So x squared plus 4, for y I'm going to put in 2/3 x, and then squared, equals 7 plus 3x times 2/3 x. Here those 3's cancel. And this squares the 2/3 and the x. So 2/3 squared is going to become 4/9. This is x squared plus 4 times 4/9 x squared equals 7 plus 2x squared, right? Because the 3's canceled, x times x is x squared, and we have a 2 in front. I don't want to have a denominator of 9, so I'm going to multiply every single term by 9. This gives me 9x squared. The 9's cancel. 4 times 4 is 16x squared. 7 times 9 is 63 plus 18x squared. Okay, I'm going to add 9 plus 16 is 25. 25 minus 18 is 7. 7x squared is 63. Divide by 7, x squared is 9. Then we get x is plus or minus 3. What I just did is I just proved that x equals 3 and negative 3 are the x values for our horizontal tangent, which is nice. And so I proved that show that there's a point P with x coordinate 3 where there's a horizontal tangent. I just did that. So I kind of wrote in, therefore, yes, there's a point P with x coordinate 3 where the tangent line is horizontal. That's what I just did. But then they go on to say, then find the y coordinate of point P. Now, this is tricky because it's just find the y coordinate of point P. It's just one point. So it's 3 comma something. It's not 2 values, it's just one of them. But it's tricky because how am I going to find that? I need to plug 3 back into the original. Right? It's kind of like, and if you did an x1, a y1, and m, that's great. So my x1 is 3, my y1 is blank, my m is 0. So now I need to find this y1. And the way I'm going to do that is I'm going to take 3, I'm going to plug it back into the original. Well, when I do that, 3 squared is 9, plus 4y squared equals 7, plus 3 times 3 is 9y. So I have a y squared, I have numbers, and I have a y. whenever I get something like this, again, I said this a bunch of times today, set it equal to 0 and try to factor. So that gives me 4y squared minus 9y plus 2 equals 0. Do whatever x method nonsense you want. And I like to kind of do it this way. 4 times 2 is 8. Two numbers that multiply to 8 and add up to negative 9 are negative 8 and negative 1. This gives me 4y minus 8 and 4y minus 1, but I need to divide out of 4. So you get y minus 2 and 4y minus 1. This part gives me y equals 2, and this part gives me y equals 1/4. Well, this kind of sucks because I'm not sure which answer it is. Is it 2 or is it 1/4? It can only be one of them. It's not both of them. Okay, so only one of those two will be where I have a horizontal tangent. And the way I'm going to do that is, well, what m did I need? I needed an m of 0. So if I plug in 3 and 2, I get an m of 0. That worked. If I plug in 3 and 1/4, I don't get an m of 0. I didn't even finish solving it because it's obvious 3/4 minus 6 over 2 minus 9 is not 0. So I know that that point P is 3, 2. Next one, very, very fast. We have a graph of f prime. Where is f increasing? That's when f prime is above the y-axis. So from negative 6 to negative 2, union from 2 to 5. Okay, why? Because f prime of x is greater than 0. You can say because f prime of x is positive for those intervals. Now the next one, D, this is the one I really want to focus on, is find f double prime of negative 5 and f double prime of 3, or explain why they don't exist. So if I have f prime, how am I going to get to f double prime? Well, we would take the derivative. And what is the derivative on a graph? On a graph, the derivative is the slope, right? The slope here. So here at negative 5, this is negative 5. I want the slope. This is a line, nice and easy. Just count down to the right 4. So the slope is negative 2 over 4, which is negative 1/2. So all I have to do is write f double prime of negative 5 equals negative 1/2. I don't need to explain anything. It doesn't say to explain it if we want the value. Okay, just that, I get the point. Now for f double prime of 3, I want to find the slope of this graph at 3. Well, at 3, we're making a corner. I can't take the slope at a corner. So this is DNE. It doesn't exist. Why? Because the graph is making a corner. But don't just say that. Say because f prime is not differentiable. That's what I really want you to see. So f double prime of 3 is DNE. Why? Because f prime is not differentiable at x equals 3. Why? Because the graph of f prime, not because the graph, but because the graph of f prime has a corner at x equals 3. Right, and then our last question. This one was really crazy. They tested it was a few years ago. I forgot what year exactly now, but like 2018, 2019, somewhat recently. And I remember all of my AP students complaining about this, and one student going, no, that was so easy. It was literally straightforward. It was just a really scary picture. And that's all it is it's a scary picture. So we're given this inside of a funnel. The height is 10. It has these circular cross sections, and at height h, the radius is given by this formula. And they say the funnel contains liquid that is draining from the bottom. Right, so draining, we're thinking that means that the height should be decreasing, right? We should get negative values for dh dt and also probably for dr dt because this would be going down. So that's a good check for you. You want to get a negative value. And we got way more bots in here tonight. Last night we didn't have any. So at the instant when the height of the liquid is h equals 3, so that's going to be one of my givens. The radius of the surface area of the liquid is decreasing at a rate of 1/5. So I know we see the word surface area or surface, and that's a little scary, but it's the radius is decreasing at 1/5 inches per second. The decreasing is important because the decreasing means that it's negative. Now the word rate, right, and the units tell me that this is not r equals, but dr dt equals. At this instant, what is the rate of change of the height? So we want dh dt. That's what we want. We want dh dt. So now we have r equals 1/20th times 3 plus h squared. I can take the derivative of this. I'm just not quite ready because of this way it's written. So I'd prefer to distribute first. That way I don't have to worry about that weird 1/20th in front. So that's r equals 3/20ths plus 1/20th h squared. And then we're going to do d dt to all of those terms. So we get dr dt equals, this derivative goes to 0. And bring the 2 down, 2/20ths h dh dt. So dr dt we know it's negative 1/5. H we know is 3. I just simplified 2/20ths to 1/10. dh dt. Like I said, very straightforward from here. Just 3 times 10 is 3/10. To get rid of 3/10, you can always multiply by the reciprocal of 10/3. The 10 will cancel, the 3 will cancel, or you can just cancel out the whole thing. So 10 times negative 1 on this side is negative 10 over 3 times 15. If you wrote negative 10 over 15, you get full credit as long as you put inches per second. If you simplify it, great, but if you wrote that, that's fine too. Right? So that is everything. For the extra practice questions, it is pretty late. And I think most of us are watching this, it's already 9:30. And, you might even be watching it after the fact and watching it either later tonight or early tomorrow. So what I'm going to do on the extra questions is let's just kind of push those to this weekend if you want to do those and you want extra practice time for this weekend or something like that. So I will go ahead and post those questions, those answers this weekend as something to practice a little bit extra. I might even give you a hard copy if you want one tomorrow. Right? So have a good night. If you have any other questions, I can stay in the chat for 1 or 2 minutes. Otherwise, have a good night, and I will see you guys in class tomorrow. Thanks. Good night, Amanda. Good night, Nayeli.